Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 26 of this course on machine learning for earth system science. This is the last lecture of module 3 where we are considering machine learning for discovering new insights in the geosciences. Today's topic is interpretable machine learning for earth system science. So the concepts which we are going to cover today are how interpretable machine learning can be used in this domain. Secondly, what is like in case of neural networks, how node activation can be used for output analysis, for the analysis of input and output, and based on that we will see other concepts like layer wise relevance propagation, backward optimization, etc. These are all concepts related to neural networks, which basically or rather which are related to making sense of how a neural network makes its predictions. So, first of all, what is explainable or interpretable machine learning? Now, these two terms, explainable and interpretable, which are often used interchangeably, though they should not be, but often they are. So, basically the idea is that, so we know that machine learning models often make very accurate predictions. We have seen that in the in several of the past lectures in this course itself, where we have shown how machine learning models are capable of making very good predictions, much better than what the classical methods would do. But the question might arise that why is it so, and which aspects or which features of a particular example are does the machine learning model focus on to make the prediction? Because the deep neural networks that are being constructed, they are like mostly black boxes. We do not know what calculations exactly happens in the nodes and the edges, etc. We see the output that we see often looks more like magic, and the climate scientists or the geoscientists who are receiving these predictions, they may be curious that why at all did the model predict in the way they did, because it is not only about making predictions, we also want to know the science behind it. We want to discover new insights about the process. In fact, that is what this module is all about. So, just making great predictions is not enough. We have to understand why those predictions were made. So, one part of that is asking for any given example, which parts of the example or which features of the example were most relevant in making that prediction, and secondly, what are the exact roles of the different parts of the model that we developed. So, if it is a neural network model, so many nodes, etc. are there, so many layers are there, what information is actually calculated by them? Now we may also be can those mathematical operations be represented in a more comprehensive way, that is or that is by a domain scientist, can they make any sense of those computations? Also, some questions might be asked that so many examples are there, so many training examples are there, each of which are mapped to some kind of predictions by whatever model we are using. So, for a particular outcome, for a particular prediction outcome, if we are doing some kind of a classification analysis, now is there something like the optimal or the prototypical input which causes that prediction outcome? And finally, what is the domain knowledge about the process that we can get from this kind of analysis? So, all these are questions related to explainable and interpretable machine learning, which we will study here through 3 research papers that have appeared mostly in the last 2 or 3 years. So, here is the first paper, physically interpretable neural networks for the geosciences, applicability for Earth system variability. Neural networks have become increasingly prevalent within the geosciences, although a common limitation of their usage has been a lack of methods to interpret what the networks learn and how they make decisions. As such, neural networks have often been used within the geosciences to most accurately identify a desired output given a set of inputs, with the interpretation of what the network learns used as a secondary metric to ensure the network is making the right decision for the right reason. This is important because it is not enough to make an accurate prediction, but rather the prediction should be done for on the basis of some features or something which are physically meaningful. Otherwise, like it becomes a case of say spurious correlation or something like that. That is not what scientists want. Neural network interpretation techniques have become more advanced in recent years. However, and we therefore propose that the ultimate objective of using a neural network can also be the interpretation of what the network has learnt rather than the output itself. We show that the interpretation of the neural networks can enable the discovery of scientifically meaningful connections within the geoscientific data. In particular, we use 2 methods for neural network interpretation called backward optimization and layer-wise relevance propagation, both of which project the decision pathways of a network back onto the original input dimensions. Let us first understand these 2 methods, backward optimization and layer-wise relevance propagation. So, backward optimization. The method input is a user defined output of a trained neural network. So, we have a neural network and let us begin with an output. So, let us say the neural network predicts the class levels, and for a particular example, let us say for a particular task the possible outputs are class A, class B and class C. So, let us say for example focus on class A. Now, the question which I am asking is, what kind of input will result in a prediction of class A, or what kind of an input will result in a prediction of class B? What is a typical input for class B? So, the method output is an optimized input that shows the input pattern most closely associated with the user defined output according to the trained neural network. It will become a bit more clear when we come to the specific examples. So, the procedure is as follows. First, the neural network is trained and the weights and the biases, all the weights and the biases are etc. are frozen, which means that they will no longer be updated. So, like the training of the neural network etc. is done, all its parameters are fixed and frozen now. Now, a desired output from the neural network is defined as obtained by as specified by the user, say class A or whatever. For example, if the network is trained to identify whether a sample belongs in one of 2 categories, the desired output could be when the neural network is 100% confident that the input belongs to those categories. Right. So, as I said again, class A, class B and class C, these are the 3 possibilities. Let us say for class A, is there any input for which the model will be 100% certain that yes, it is indeed of class A. So, that is a typical input, like we can say a typical prototypical input for class A as far as the model is concerned. Now what we do is a sample is generated of the same shape as the samples used to train the neural network, but the sample is all initialized as zeros. So basically it's like if it takes the 0 vector, if it takes m cross n matrices as input, the neural network, then we start off with a like basically we are trying to estimate the values of x. So let us start with some x which is like all zeros initially. This all zero sample is passed through the network and the output is generated. The output is then compared to the desired output and the loss of the all zero sample is calculated with respect to the desired output. So for the all zero sample, some like the network will make some kind of prediction. That prediction is compared to the particular output we have in mind, for which we are searching for the optimal input, and so they are compared and some loss some value of the loss is calculated. Now the loss function is the same function as is used to train the network. The loss is translated backward through the neural network to the input layer using back propagation. But rather than updating the weights and biases of the network along the way, the input sample itself is updated in a manner which reduces the loss using an increment of the information or gradient that was translated back to the input layer. So like in normal back propagation, the input remains constant, but it's really the weights, the w's, that are updated through gradient descent. In this case it's the reverse. In this case we will assume that all the w's, the weights, they remain unchanged, they are fixed at the values that was obtained by the process of training, but rather it is the input values x that are going to be updated when we do the back propagation. So the variable is no longer w, but instead x itself is now the variable, and they are going to be, so the input value to every node is going to be updated like as the error is back propagated. And so that is why this updation of the input values will take place from the output to the input. So these steps are iterated, the steps 4 and 5 are iterated until the input is optimized such that the iterations no longer reduce the error, that is basically it converges. So just like in the in normal back propagation, like we say it has converged when the w values no longer change. In this case we will say convergence has happened if x no longer change. So here is a cartoon which shows the illustration. So let us say that this is the neural network. So this is like, for simplicity let us assume that there is only one hidden layer with these two variables, and so like these are the different edges whose weights have already been estimated, and this is the output layer. So like there are let us assume say that these indicate the probabilities of the two classes that let's say that it's a binary classification problem. So there are two classes, and these two output nodes, they indicate the relative probabilities of the two classes. So here is let us say that the desired output is 1 0, that is class A is I have basically I want to see the prototypical input for class A. So that means a situation where the first node which represents class A, that has full probability 1, the second node which represents class B, that has probability 0. So I am looking for the input which causes 1 and 0 at these output variables. So as discussed here, we start with the all zero samples. So this is the all zero sample, it is provided as the input. So all the calculations take place, and let us say we find the output values come to 0.1 and 0.9, which is of course very different from 1 to 0. So we calculate the loss function. Now since this is a classification problem, the loss function is probably the cross entropy loss function. So this is a probability distribution over the classes, and this is the desired probability distribution. So two probability distributions can be compared using the this thing using the cross entropy. So we get the loss value of 2.3. So now this loss is now going to be back propagated through all these through all the nodes like this from the output towards the input. So, like as I said, as the back propagation happens, it's the input values which get updated, not the weights. So, so based on these 0.1 and 0.9, first these two nodes, their values get updated, then these two, then based on their values, the values of these two nodes get updated, and finally the input values also get updated. So let us say that this becomes the updated input values 0.2, 0, 0.1. Now we just keep on iterating like this over and over. So let us say in this case, when we use this as an input 0.2, 0, 0.1, again by using this as an input, let us say the output changes to 0.8, 0.2, but that is still different from the desired output 1 and 0, some residual is still there. So again that error we calculate, and again we back propagate it like this, again updating all the input values but keeping all the weights constant. So let us say after that we get these as the updated input 0.31, 0.2. Again this and in this case the loss is 1.61. So this is better than the loss we had obtained in earlier, which was 2.3. So we just keep on doing this until the loss is very nearly equal to 0, and then we find that whatever the input we get like that is the desired input. That is, we see that for the input of, in this case 1.5, 0.3, 0.8, the output prediction is class A, probability is 1, class B probability is 0, and this is exactly what we desired. So this is then a prototypical feature vector which will be confidently classified as class A. Similarly for class B, where this one has 0 value and this one has 1 value, we can calculate the prototypical example. Okay, so this is the task of backward optimization, where for a particular output we try to find its input. The next task is layer wise relevance propagation, which is like in this case the input is an input sample, and the method's output is the relevance of each feature within the input sample for the associated output. That is, so when the input is presented, the neural network which you have created, that will definitely give some output, but which of the input features was actually most crucial or most important in determining that particular output. So if you look at this neural network, so like here, let us say that this is my input x1, x2, x3, and once again there is no optimization of the weights to be done. That is, the neural network has already been trained, all the weights etc. are frozen. So now let us say that when we provide x1, x2, x3 as the input, the output is found out to be y1 and y2. So now I will be, so there are two output nodes. So now what I am interested is that what is the relative importance of these features in choosing the creating this value of y1. That is, which of these features determined that this particular output node is going to have the value of y1 instead of some other value, or for this node, which are the features which ensured that its value was y2, right. So for that what we do is layer wise relevance propagation. That is, we calculate some quantity known as relevance, and then we propagate it backwards like that. So like when so the initial let us say we are focusing on this particular node and we are trying these particular output nodes. So let us say the relevance value is initially set to this y2 value itself. Now according to that, this value is connected to these input nodes, then this input node is connected to these two hidden nodes etc. So so whenever we see this kind of a situation, that is two successive layers I and j, in the jth layer I have a value whose relevance I mean there is a node whose relevance I know or have calculated. Now that relevance I have to propagate back to the connected nodes in the previous layer, and for that we have a rule for propagating these relevance values. Initially this one will have its relevance value, which is the output value itself. Based on that, in this node we will calculate the relevance value according to the formula. So see, Ri for any node I which is in, let us say, in any layer, I am calculating that relevance value Ri in terms of Rj, which is the next layer towards the output. So from the output, again the relevance values are flowing backwards towards the input according to these formula. So that way, for starting from this output node, we calculate the relevance values for all the nodes that lie on its path back to the input. So that way, like for the input variables also, or till the input variables, these relevance value is back propagated. And so these relevance values, what they give us at once they reach the input variable, the input nodes, what they give us is the something like the relevance of the different inputs. So these are all conceptual ideas of interpretable or explainable machine learning. Now their application in the domain of earth system science. So we consider two problems. You can say that they are something like toy problems, I mean, which are not really the biggest questions of in earth sciences, but they mostly they are for demonstration purposes. So the first problem is the El Nino southern oscillation is a phenomena in the central Pacific Ocean, where a particular part of the central Pacific Ocean known as the Nino 3.4 region, that gets very hot in some years and very cool in some other years. So those two, so it's like there is a oscillation in a phase. There is a positive phase when it is very hot, that phase is known as El Nino, and then there is a negative phase called La Nina when that region becomes cold. Now this is like a very fundamental thing, concept in or very fundamental phenomena in climate sciences, in the sense that although it happens in central Pacific Ocean, but its repercussions are felt all over the world, in different parts of the world. So the input is a special map of the sea surface temperature anomalies all over the world on any given day or any month. And the output is the probability of the El Nino or the La Nina phase on that particular day or month. That is, we know that what happens in the central Pacific, it determines or it influences the sea surface temperature all over the world. So the question is that is being asked is, suppose in a given month, let us say January 2022, this is what the sea surface temperature all over the world looks like. Now based on that, tell me, are we currently having an El Nino or are we having a La Nina? Okay, so that's the output probabilities. This is the first problem we will consider. The second toy problem we will consider is like the temperature, let us consider the temperature anomaly or specifically the sign of the temperature anomaly, like positive or negative, on a particular continental region, that is some location on the land, let us say Kharagpur. So let us say today is okay, let us say you have the sea surface temperature anomalies from all over the world. Based on that, you have to predict whether today in Kharagpur is going to be hotter than usual or colder than usual. That is, are we going to have a positive temperature anomaly or negative temperature anomaly. This can also be cast as a seasonal prediction problem. Instead of a daily anomaly, we can consider as monthly anomaly or something like that. So is it a hot time in Kharagpur or is it a cold time in Kharagpur? That is what you have to understand based on the sea surface temperature anomalies on all over the world. So these are the two problems for which both are basically something like binary classification problems. So we train a neural network for that. In both cases, the input is the world map of the sea surface temperature, and the output is like one of two values, or rather we can say the probabilities of the two classes. So we have already seen how like the spatial map of a particular variable, in this case sea surface temperature, can be provided as the input. So there will be convolutional layers and all kinds of things. So let us say that instead of going for a let us say we have built some kind of simple neural network which is capable of doing this prediction reasonably well. Now the question I am asking is, suppose based on the world map of sea surface temperature anomalies, it is actually able to predict like is it El Nino or is it La Nina. Then the question is exactly which that is I may be interested in asking for what kind of pattern of the these temperature anomalies over the world will I be certain that it is indeed El Nino or it is indeed La Nina. Similarly, in the second case also, suppose like it is a hot day in or a hot season in the location that is like that is being investigated. So then like what kind of a spatial map of these sea surface temperature anomalies will make us most confident that it should indeed be a hot day or it should indeed be a cold day at the location that we are interested in. So like in these maps they have indicated the location by a red dot. So this is what the answers to the questions is. So if you in the first problem of ENSO phase prediction, so this is what the optimal output looks like. So optimal output, so basically it shows that it might be taking the whole world's sea surface temperature anomaly as inputs, but while predicting whether there is ENSO or whether there is El Nino or La Nina, it is really this part which it which it is focusing on. Similarly, if you look at the layer wise relevance propagation, where like in different parts of the, or different input features you are checking its relevance. So you can see that so this black value means low relevance and this white value means high relevance. So you see that it is the observations in this Central Pacific region, these are the what have the high relevance in predicting whether it's an El Nino or La Nina, while the others other features they have no relevance, little or no relevance. So in a sense it is like telling this is like this should this answer should be obvious, because we know that El Nino happen or La Nina happens due to a hot phase of in this particular region only, in the Central Pacific region, which is known as Nino 3.4. So if we have to understand from sea surface temperature anomalies, if we have to understand whether it's El Nino or La Nina, then we should be focusing on this region only, not on any other region. That is commonsensical, but that common sense had not been communicated to the model in any way. It was just given maps of the sea surface temperature all over the world, and it had been informed that this is an El Nino phase or this is a La Nina phase. The model is itself able to understand that it is because of this region that you are calling it either the El Nino or the La Nina. Similarly, in case of layer wise relevance propagation also, it's precisely these locations which have the relevance, not any other location. If, this is something which is which the model did not know, but it is able to figure it out from the data. Similarly, in case of the seasonal prediction problem, we find that the optimal, if we are focusing on this particular region along the western coast of Canada, let's say it's a hot day in the western coast of Canada, then what does the spatial map of sea surface temperature look like? And this is what is shown. And similarly, when we are calculating the composite the relevance, we see that the it's really these regions, the southern Pacific, or the we can say the south central Pacific Ocean, as well as some regions of the Pacific Ocean here, which have the most relevance in like determining whether this location of interest is going to have or is having a is having high temperature or not. So, this is the result we get for this location. If we consider some other location like Kharagpur, as I mentioned, then we may get some other result. So, like these are the more detailed maps of the of those relevance. Now, this is what we discussed here is one kind of one method of calculating the importance of features and so on. Another method of importance of the features is the permutation feature importance. So, let us say we have a feature vector x with these particular, like it is a d-dimensional feature vector with these values which produces the output of y. Now, suppose I replace one of these values, let us say the first feature, its current value is x1, let us say I change it to some other value, I make it x1 prime, then the y should change, but by how much? I measure that change, and then I do this kind of thing for all variables, and I see that changing which variable has the maximum impact on the output variable y, and in fact like changing by how much has how much effect on the output variable y. So, the idea here is that the variables which cause maximum change in y, they are the most important variables, at least locally. That means, for these values of the other variables, this feature is most important. For some other values of the other variables, some other feature might be most important. So, we are basically looking for the locally most important feature in this situation. So, that is the permutation feature importance. So, like in this paper, what they have tried to do is the probability of severe hailstorms, that is, like suppose a thunderstorm is going to take place, so they are calculating what is the probability that hailstorms will occur. So, these are the inputs like the geopotential height, temperature, dew point, zonal wind, meridional wind, etc. All these are inputs to the neural network. Based on that, the neural network estimates the probability that there is going to be a hailstorm. So fine, the neural network is trained, and it, let us say, it performs quite well, and as has been found out by this study, it performs better than the other methods like logistic regression, etc. But then the question is, why did it predict so? So, the authors of this paper, they have used permutation feature importance to find out like really which are the which are the features that resulted in the prediction of these things. So, like for each of the variables like which of the for each of the input variables that were considered, their their relevance values are, or rather their this permutation feature importance values are calculated, and similarly, like we have some other interesting applications of these things. So, like detecting climate change signals using explainable AI with single forcing large ensembles. So, here basically the idea is that so we all know that the temperature across the world is changing due to global warming and climate change. Now, if you are provided the and this and we know that the earth has been gradually warming up since the 1900s and so on. So, now if you are given the temperature map of the world, then from that map can a neural network predict which year that map belongs to, and if so, if it can indeed predict, then which are the most important regions which will be looking at. That is, in a sense, it is like asking which are the regions which have contributed maximum to the global warming from 1900s to say the current times and so on. So, so that is what is achieved by this kind of task. So, like it is found that they have trained a neural network in which instead of focusing or predicting the exact year, they predict the neural network can predict some year range, like which decade, let us say the 1920s decade or 1930s decade and so on. So, it turns out that this neural network is once it receives a spatial map of the temperature over the world, it is able to predict the decade from which this map was taken. It is able to predict that quite accurately, but then we do the layer wise relevance propagation etc. to find out which are the locations having maximum relevance. So, it turns out that like as you can see that the regions which are marked in white, they are the maximum like they have the maximum relevance. That is to say, from let us say from 1900s to the current times, it is these regions which probably have had the most significant changes, and hence by looking at it's by looking at them that we can understand most clearly which year it is or which range of year it is. And so, like this kind of study can be done for different variables, I mean not only for temperature, but let us say also from the aerosol distribution all over the world, or the concentration of different greenhouse gases from all over the world etc. And of course, for different variables we see different amounts. So that brings us to the end of this module. So these are the different papers that we discussed today in today's lecture. The key points to be taken from this lecture are, first of all, most predictions by machine learning in earth science applications, they can be explained by only specific parts of the input, and this which provides new domain information. Like in this case, only certain locations which carry most of the information behind the prediction. Actually, like for the different year groups in this case, in the last problem that we mentioned. So these are the for each set of years, say for the 1920 to 1959 region, decade, it's really this is what the optimal maps of or the optimized inputs for the aerosol map, for the greenhouse gas maps etc. look like. Similarly, for the 2000 to 2039 year, this is what the optimized maps look like. So these actually give us the domain knowledge in the sense like how these maps have changed over time, and like which of these maps is the distinctive characteristic of this particular decade. Often the prediction classes or values, they have a typical or typical input, which is what we are calculating by the process of backward optimization. So we also, these explainable AI techniques help us to understand the weaknesses and the biases of the different models, and also help us to unearth such domain information. So with that, we come to the end of module 3. From the next lecture onwards, we will move to module 4, where we will see how machine learning can help in the earth observation systems. So till then, bye.